Good enough.
We then started going over, the slope of the cosine curve. We got to that.
So if I have a position graph equal to cosine of 3t, we'll throw an I at it. What would be the velocity graph?
By 3.
Okay, stretched by 3. All right, so put a 3 out front. It's doing slope, so it comes after cosine. No, as in, if I have a cosine curve,
Oh, negative sine.
negative sign. So negative sign, and then 3t. And the acceleration graph? That I hat's just in the way. You can make her do it all? Luis?
Well, I'm thinking in terms of like derivatives and stuff. Would it be like -9 cosine 3t?
Yeah, because after sine comes cosine, so the negative's not affected by it. So cosine becomes negative sine becomes cosine, so the negative stays there. The next one, if I did the jerk, that would be -27, because then every time I take whatever's multiplied times t and I multiply times what I have on the outside, and then cosine becomes negative sine, so that would cancel out, and I'm left with sine, 3t. And then the coefficient changes, but then it goes back up to cosine, negative cosine, sine, and so forth. If I have y is equal, let's not use y and x, let's just use p and q. P is equal to the cosine of q. So if I graphed it, let's see, this would be my q axis and my p axis. What is the wavelength? Did you get that?
There's nothing stretching. I don't know. Random guess.
If you think about the unit circle, as we often do, unit circles circle the radius of 1, and any point on here, any point x, y, so this distance here is x, that distance there is y, that distance, that angle right there is theta. The x value is going to be the cosine of theta, and the y value is the sine of theta. So if I imagine that I've got sort of a spinner here that's rotating around the circle. That graph right there just points to the x value. The x value starts out large. If I'm starting here, and going around like that, and going around like this, the x value starts out large, it gets smaller and smaller, x becomes negative, -1, keeps going, x is 0 again, x is 1. So it's just whatever basically the projection onto the x-axis, more efficiently. So when it's here, I project down onto the x-axis, that's the cosine value. I project onto the y-axis, that's my sine value. What is a wavelength? And this is a question for 151.
One cycle of, I kind of remember.
It has something to do with one cycle.
Is it the distance between two crests?
Okay, yeah. So it's a length, wavelength. It's the length, it's the distance a wave travels in one period or one cycle. So if I have P versus Q there, what's the wavelength?
Two pi.
So you're saying that when Q is equal to 2 pi, I'm back to where I started.
Yes.
Yes. Yeah, you're right.
I'm gonna be honest with you. I was gonna start guessing pi, 2 pi, pi over 2.
You would have eventually gotten there.
Yeah.
It is 2 pi. So when Q becomes 2 pi, in other words, if I look at that angle, when that angle becomes 2 pi, I'm back to where I started here. 2 pi radians, full circle. All right, so the wavelength is 2 pi. Do we accept that? What's the period?
Pi over 2.
Why?
I'm guessing.
What is the period? In general, the definition of the period.
It's like, all of these things are in my brain, Dr. Fox, but they can't come out.
Okay, I can accept part of that.
My brain's like thinking of all of the like equations and stuff. I just can't remember what any of the symbols I'm thinking of mean.
All right, if it helps any, the symbol for period is a capital T. And to flash back, the reason why I don't use capital T for tension. All right, first off, why T? It's a capital T, but why T?
Time?
Yeah, period is a time. Time for what?
One cycle, one
Yeah,
completion, whatever.
for repetitive motion, it's the amount of time it takes to do it once. So if this thing is spinning around, then it's the amount of time it takes for the spinner to go all the way around back to where it started. So, for this wave over here, what's the period? I thought that was the wavelength.
I also am thinking 2 pi.
But isn't 2 pi the wavelength?
See, what I'm thinking is like, I'm remembering an equation, and it's like A cosine, or A whatever, and then B, and then the thingy plus C, and I feel like I remember period being wavelength divided by whatever B is.
The thing in front of the time coefficient?
I don't know. I'm just like,
All
I'm
right, so
hazily
what I think-
remembering things.
If I am interpreting that correctly,
What I think you were saying is that if you think to the lab quests and you're measuring oscillating motion, it will give you an equation, y equals a cosine dt plus c plus d, something like that.
Yes.
Is that sort of where your head was?
Mm-hmm.
All right, this is the amplitude.
Yes.
Right.
This is the angular frequency. I don't know why I bother writing it since I'm not going to write it legibly, but angular frequency. This is the phase shift. And this is basically how far up and down. It basically establishes,
Mm-hmm.
I guess, vertical
It's a vertical.
baseline. And so you're thinking that the period was 2 pi divided by whatever's in front of t?
Yes.
Okay, that is correct.
Yay! I love being right.
So over there, 2 pi, is that the wavelength or is it the period?
It can be both. It's
Pardon?
multifaceted. It can be both.
No. I mean, not with as little information as provided, it won't be both.
Is it?
It's,
I remember doing these type problems where you get the equation and the question is, what's the wavelength, what's the period? Free cal, my recollection, it's been a few decades, but my recollection was free cal.
Yes.
And I I do not remember there ever being confusion about whether it was 2 pi divided by whatever was in front of the independent variable. But now I'm asking you, how do you know if there's a 1, implied 1 in front of q, it's going to repeat itself after 2 pi, all of that is correct. How do you know if that is the period or the wavelength?
you don't?
There is a big tell about whether it is or not. If you recall, if I have the cosine of something, what is in here has to be either radians or degrees or radians or some sort of angle measurement. Because we are a pool, of course, we're talking radians. So whatever's in cosine of whatever you're doing has to be cosine, we're doing radians instead of degrees. So if I have 3t in there, cosine of 3t, like I have written over there, what are the units of the 3? SI units.
Seconds?
If 3 is in seconds and time is in seconds, then I'd end up with seconds squared, so that's not gonna give me a radian.
Revolution?
What is the radian in other terms of other units? Not degrees, so in terms of SI units.
It's just radians.
Somehow I feel like I don't know the answer.
Huh. I think you might be in company. This might be a read my mind exercise, in which case, all right, please, pick it up. You picking up what I'm throwing down?
No, I had coffee yesterday.
All right. A radian is a unitless unit. Hopefully that expression rings some bell. If you think back to the equation S equals R theta, the arc length is equal to the radius times the angle in radians. If S is a distance, it's an arc length. R is a radius, it's a length also. So that's a length and that's a length, and the only way that radians can exist is, well, if that's in meters and that's in meters, this has to be unibus. But we use the term radians for clarification purposes. If I said an angle was 30, it said nothing else. You don't know whether I meant 30 radians or whether I just forgot to say degrees. So that's the purpose of throwing radians in there, is just for clarification. So if you think of radians though as unibus, which means that the 3t has to be unibus. So t, if that is in seconds, what are the units of 3?
There are none.
I missed what you said.
There are none.
Well, if there are no units of 3, then I'd have 3 times something in seconds, so I'd end up with seconds, and it's hard to take a
Oh, right.
cosine of seconds.
Mm-hmm.
The units of 3t are the units of, have to be the units of the angle, which is radians, which is unibus.
Uh-huh.
So the units of 3 times the units of time have to equal 1. So the units of 3 have to be 1 divided by the units of time, which is a 1/second.
So it is just, okay.
If you prefer radians per second, or inverse seconds.
Yeah. Yep.
So, in this particular case, I got 3 in front of time. The units of 3 are 1/seconds. If I did 2 pi divided by that 3 inverse seconds, I'd end up with 2/3 pi seconds. Here's my number, whatever that ends up being, a little bit more than 2, and then units of seconds. Flashing back to when Luis was saying the period is something to do with 2 pi divided by whatever was in front of, basically divided by b here. I did 2 pi divided by b, I get the period. If I did 2 pi divided by 3 inverse seconds, I get some number seconds, which would be units of period.
So if I did 2 pi divided by 1, in this case, I get 2 pi. But what are the units of this 1?
Verse seconds.
What are you assuming?
That is the period. Wait,
If you're saying the units of this 1 are inverse seconds, what are you assuming about the units of q?
that they're in seconds.
Oh. So, if q is in seconds, if q is a time, then 2 pi would be the period. If q is in meters instead, this is the wavelength. We are now branching, so when we, in 151, when we were dealing with harmonic motion, we were only looking at time. So it was 2 pi divided by the coefficient of b. The motion sensor measures position with respect to time. And so it was time all of the time. But now we have to be a little bit more sophisticated. We can no longer look at a wave oscillating in just time, because these waves are traveling. I take my electron, I move it, oscillate it back and forth, creating a fluctuating electric field, which creates a fluctuating magnetic field, and off my electromagnetic field goes, or electromagnetic wave goes. So if you think about this wave that is oscillating, so you got a wave here. Yeah, the hand motion's perfect. I got this wave here traveling like this, moving along that way.
So think about the wave when it hits Luis's head. Yes, that's exactly what's gonna happen. Which is why he's sitting down in class, because the electromagnetic waves coming from the ceiling are keeping him down. So we have this wave that's moving along. At his chin, the wave might start out, when it first hits his chin, it might be down here, but then it's gonna move up and then down and then up and then down. So at that position, it's oscillating with time, but at every place it's oscillating with time. So every position it's oscillating with time. And so if I needed to describe the wave, I need to take into account position and time. And so the big question is, how do you take position and time into account?
By the way, I asked the same question to the 252 students and gave the same basic response that you gave me. Because in math class, whichever one they ask for is the one that you have. They don't deal with traveling waves. And at least that was not my experience.
Just reassuring.
This class is so much fun.
So to deal with position and time, we need two variables in it. So I'm going to define an electric field is equal to some maximum value, that's my amplitude, times the cosine or sine, whichever one you feel like, kx minus omega t. And we could tack on a phase shift if you wanted. I don't want to. And we could tack on a vertical shift. We'll assume that they're both zero.
And the EM, it stands for the maximum of the.
Maximum electric field strength. So this is the electric field. This is maximum electric field strength. Omega, we dealt with in 151 in harmonic motion. This is the angular frequency. Scroll it over on the right board, angular frequency. And K